Hello everyone, this is Professor Keen. We've been doing some practical lectures lately on how to solve problems using Newton's laws of motion. In my last lecture, we talked about how to figure out the coefficient of friction required to hold a block steady on a ramp. I'd like to say a few more comments about this before we move on to one more problem. So if you'll remember last time in our discussion, we talked about having this ramp, and in order to solve this problem, we drew a free body diagram for the block of mass m sitting on the ramp. You might recall the free body diagram, which consisted of three forces. One force, which was the normal force exerted by the surface of the ramp up on the block. Another one was the weight of the block. And the other one was the frictional force that is acting parallel to the surface of the ramp. And we set up a coordinate system. We decomposed the weight into a weight in the x direction and a weight in the y direction. This was the force. And we found out that in order to use Newton's second law of motion, this normal force right here had to exactly be balanced by the weight in the y direction, so that these two forces summed to zero, so there was no acceleration in the y direction. And furthermore, we found that these two forces had to be equal to one another, so that there was no net force or total force in the x direction, so that the acceleration in the x direction was zero. And when we set up those equations, we found that the coefficient of friction required in order to keep the block stationary was equal to tangent of theta, where theta is the angle of the ramp. So that's just summarizing what we had done last time. What I want to do this time is just say one more thing about this. Excuse me. So let's suppose if suddenly the coefficient of friction was zero. So suddenly, maybe this surface was coated with ice and it froze, or water, and it froze and it turned to ice, and suddenly it became very slippery so that the coefficient of friction was zero. What would happen then is that the frictional force, which is equal to mu times the normal force, that because mu would be zero, the frictional force would be zero, this force right here would go away. And so let me erase that. So imagine if suddenly this frictional force vanished. What would happen if the frictional force vanished? Well, then the weight in the x direction would be unbalanced, and so the x direction force, that is the sum of the forces in the x direction, would just be a single force, and that would be equal to the mass times the acceleration in the x direction. And solving for the acceleration in the x direction, we can find that the weight in the x direction divided by the mass, the block would accelerate in this direction, right? And you might recall that the weight in the x direction was equal to the total weight mg times, mg times sine of theta divided by m. So this is the weight in the x direction. And you can see right away when you do this, the acceleration in the x direction, the m's cancel out, and you get g times sine of theta. So if suddenly the frictional force vanished because the coefficient of friction became zero, then the block would accelerate in the x direction, and Newton's second law would allow us to figure out what the acceleration would be. And it would just be equal to g, the normal acceleration of gravity, multiplied by sine of theta. So if you remember sine of theta, what does sine of theta look like? Here's sine of theta versus theta. Sine of theta looks like this, right? So this would be pi, and this is 2 pi. So if theta is zero, so the acceleration in the x direction is g sine of theta. If this theta is 0 degrees, that is the ramp is horizontal, sine of 0 would be 0. So if theta equals 0, then the acceleration in the x direction would be 0, right? That kind of makes sense, because when it's horizontal, it wouldn't accelerate down the ramp at all. If theta was, let's say 45 degrees, then sine of theta, well, at, 90 degrees, it's 1. At 45 degrees, it's 1 over root 2. So sine of theta is 1 over the square root of 2. And then the acceleration in the x direction would be g over root 2. It would just be some fraction of the acceleration of gravity. And finally, as theta goes up to 90 degrees, if theta equals 90 degrees, what happens then? Well, 90 degrees would be right here. Sine of theta is 1. Then sine of theta is equal to 1, and the acceleration in the x direction would just be g, which kind of makes sense. That would be the object falling straight down, because it'd be a vertical ramp. So all this stuff sort of makes sense with our intuition about what should happen to the acceleration of the block as we increase the angle theta. Okay, so now what I want to do is say a few other things about another problem, and what I'm going to do is I'm going to drag this over to here. Let me do one more example problem before I move on from friction. So this is going to be example 4. And this one is not going to involve very many calculations, but I think it's an important conceptual problem for you to understand. So here's the question I would like to ask. Is if you have a car, let's suppose you're sitting in a car at a stoplight. So here's the car. There's the wheels. Some kind of fancy sports car like this, okay? So here's your car like this, okay? And you're at the stoplight, and suddenly the light turns green. So you get a green light suddenly, and you hit the gas pedal. So you hit the gas pedal, and the question is, when you hit the gas pedal, what are the forces, or what is the force on each wheel, or what are the forces on the wheels due to friction if the car is rear wheel drive? So I'm not asking you to draw a complete free body diagram. I'm simply asking you, what is the direction of the frictional force exerted by the road on the back wheels and on the front wheels if your car is a rear wheel drive car? Okay, so let's do this. Let's think about the wheels separately. Let's first of all consider the back or the rear wheels. Okay, the back or the rear wheels. So let me just draw a picture of this back wheel. And what happens when you hit the gas pedal? Okay, so when you hit the gas pedal, your engine turns and the axle immediately begins rotating. And so this is the forward direction. That's the direction you want to go, right? What happens is wheel, because the engine fires up, this wheel begins trying to spin, right? And when it tries to spin, it's trying to move in this direction at the bottom, right? So that's the rotation direction that the bottom of the wheel is trying to move. And so you might correctly realize that it is going to try to push the ground to the left. So the wheel exerts a leftward force on the ground. That's the frictional force exerted by the wheel on the ground. So this is due to friction. But notice that this is not what I'm asking in this question. I'm not asking what is the force on the ground. I'm asking you what is the frictional force exerted by the ground on the wheel, right? And if the wheel is pushing the ground to the left, then by Newton's third law, the ground must be pushing the wheel to the right. That would be the equal and opposite force exerted by the ground on the wheel. So the friction force on the rear, so the friction force due to, or maybe I'll say exerted, friction force exerted on the wheel by the ground is rightward. The ground is in fact trying to push the wheel to the right. Okay? Now, what about the force on the front wheels? What is the force exerted by the ground on the front wheels? So what happens? So here's the picture of the front wheel. Now I already said that this is a rear wheel drive car. So this rear wheel is trying to spin in this direction, okay? But the front wheel is not trying to spin due to the action of the engine. Rather, because the ground is pushing the back wheel forward, the whole car is going to be thrown forward. When it's thrown forward, the car, which is connected of course to the front axle, that axle begins to move in that direction. And if the wheel was stationary compared to the axle, the whole wheel would sort of slide to the right. And so what happens is the frictional force exerted by the ground on the wheel tries to prevent this sliding to the right of the wheel. And so as a result, there is a friction force exerted by the ground on the front wheels. That's the friction force exerted by the ground on the front wheel. Notice that the frictional force is in the backwards direction on the front wheels and in the frontward direction on the back wheels. And the idea, of course, is that this friction force tries to prevent any relative motion between the wheel and the ground. The wheel is trying to slide forward, and that friction force is aimed backward to prevent the wheel from sliding forward. Here, the wheel is trying to rotate this way because the axle is turning, so this wheel point is trying to move backwards, and the friction force is in turn pushing on it forward, trying to prevent that relative motion. Okay, so I think this is an interesting problem because it illustrates the kind of a complicated situation that requires very careful thinking about the directions of frictional forces. I would encourage you to try to do the same problem on your own, but thinking about if your car, for example, was a front-wheel drive car and you hit the gas pedal, which direction would the frictional force on the front wheels be, and what would the direction of the frictional force on the back wheels be if it was a front-wheel drive car? In this problem, I did a rear-wheel drive car. One other thing that might clarify this for this problem that I've just worked out is if you consider what happens if you weren't driving on pavement, but you were driving on, let's say, ice. What happens then is that when you hit the gas pedal, this back wheel begins spinning, but because there's no friction, the car is not thrown forward. The friction force is very tiny. In fact, in the ideal case, with no friction, there would be no friction force, and the car wouldn't lurch forward at all, because all what happened was the wheels spinning. Okay, I think I'll stop there, and we can pick up more of this discussion on Newton's laws next time.